Oh, Professor,
Yep. Go ahead.
Professor, can you hear me?
Yes, can you hear me?
Yeah, this is Mohammed. How are you?
I'm doing well.
Yes, Professor, actually, I have the question or the quiz. I did understand Alex is very good and Connor is very good. I did dominate the topics. What I didn't get in is a good score for today. I think the problem is the final answer or significant digit. I have no idea, but I'm worried
So
about.
just to clarify, for all of our quizzes, I always double check. So if it's a rounding error, I will fix it. So don't worry about what the score is right now. The score will be finalized sometime by the weekend. So I always double check things.
Okay, thank you so much,
Okay,
I'm responsible about that. Thank you so much.
no problem. Okay, so let's get started. Just a quick check, mic check. Everything's good? You can hear me?
Yes.
Okay, awesome. All right, so we're going to pick up where we left off. Did we finish this question? Anybody remember? Let me go back a slide so you can see it. Nobody remembers? It's been too long. Okay, we'll go through it just in case again. If we look at experiments 1 and 2, I don't need to worry about CO because they stay the same. So how this changes is 4 times bigger. How this changes is 16 times bigger. So essentially 16 is equal to 4 to the m power. And with that said, m is equal to 2. Any questions? Okay. Now with that done, let's go ahead and compare 1 and 3. So NO2 stays the same, so I don't care about it. This has essentially doubled, but this stays the same. So this is 1 times. So 2 to the n power is equal to 1. So n is equal to 0. Any questions? Okay, with that said, I'm going to go to a page that is a little more clear. So we're going to go ahead and look at this equation here. I can essentially plug anything I want to plug in right here for my rate and for my NO2. Oh, not NO2. Yeah, for NO2. Okay. So not this one right here, that's CO1. So whatever my value is for NO2, I can plug that in, algebraically solve for this K. Any questions on that? Okay. Now, with that said, I do want you to memorize this stuff right here. Or if you can calculate it, you're welcome to calculate it. So this is the units for the rate constant, depending on what our overall reaction order is. So what this means is if I go ahead and write this down, let's write the word rate here is equal to your K. And then we'll say this is A, whatever it is, okay? And then we'll say there's a B. So if this is to the 0 power, this is to the 1 power, there is only one order here, okay? And what that essentially means is this is your moles per liters, this is your moles per liters times seconds. And so when I move this to the other side, in order to algebraically move this, I need to multiply this by liters per mole. So this gets canceled out. When I put liters per mole here, these get canceled out. All that's left is just 1 over seconds. So for K, if there's only one of our overall order, the units should be 1 over seconds. Does this kind of make sense so far? I will take your silence as a yes then. So let's try a different scenario. Let's imagine that you had the same exact situation. So we have rate is equal to K, and then I assigned A and B here. Let's say these were both 0. Okay, so they didn't have any of these. So my rate, the units for my rate is the same as my K. So then essentially it is just this one right here, because my rate here is moles per liters times seconds. So it would keep the same units. Okay, does anyone else need more time to copy that down before I clear it? All right. Now let's do the other two. This is where it gets a little more complicated, just in case you weren't following along. So I'll rewrite it on top here. Rate is equal to your K, and we'll say this is A, and this is B, okay? So we'll say this is 1 and 1. So in total, there is 2 orders, a total order of 2. Now, when I move it to the other side, again, these are moles per liter. And this one is moles per liter times seconds. So I move it to the other side, I must multiply this by liters per mole. So the inverse of it. So that gets canceled out. I must multiply this by liters per mole, same thing. That means I'm multiplying this side by liters per mole twice. So this one gets canceled out. The new units for K is now liters per mole times 1 over second, which is exactly what is here. And that is a unit for K. And the last scenario, I'm just going to go ahead and clear the screen now, is when we have the last one here. So essentially, I'm going to write this again. Rate is equal to K. We'll call this A, and we'll call this B. And in this scenario, I have 2 and 1. Okay. So same things here, moles over liters, moles over liters, moles over liters times seconds. So this one is actually moles over liters squared because there's 2 of them. So again, in order to clear them out, I need to multiply by liters over moles. So in total, I have 3 of these. So 3 liters, liters cubed to moles cubed. So it gets rid of all of these here. And then this gets rid of it over here. So I finally move it to this side. It's cubed and cubed. And now I can cancel out one of these, it becomes 2, and get rid of this. So what's left over on this side is liters squared over mole squared times 1 over seconds. And that would be the units for K. And this is not even solving for the number of K. You still need to solve for the value of K. But in terms of the units, this is what you should be getting. Anyone have any questions up to this part?
Is B always 1?
No, we can essentially, this can be 2, this can be 1. Any of those numbers. I just decided to use 2 and 1.
So it's like the reaction order. So if it's like
The
2,
total
then
order,
it would be
yeah.
1, 1.
Yeah, overall would be 1, 1. So this is 2, then it'd be 1, 1 here. If it was 3, then it'd be 1, 2 or 2, 1.
Okay, and then we just use basic mathematics and
Yes.
okay, get the units.
Okay. So the reason why I want you to memorize this is because they will ask you questions. I'm going to give you an example here. What is the overall order of, we'll just say this reaction with a rate constant of, and then give you a number. We'll say like 45 seconds minus 1. That's what they're going to tell you. And with just that information alone, you should be able to answer the question. What is our overall order here?
1.
First one, right? Because we see it matches with this. So the overall order is to the first order. That's just based on what the units are here. Any questions? Okay. So let's continue. We're going to now talk about the integrated rate laws. So previously, all of the rate that we didn't really involve time. We just looked at an experiment, we wrote it as with seconds, but we didn't involve time. Here, the integrated rate law actually uses time as a variable. So there are 3 equations here that you will want to kind of memorize. There are different ways to write this equation. I will show you the line method, so it's the easiest one to remember. These are essentially the equations. If you know how to manipulate the equation, you're welcome to write this down, memorize it, and move forward from there. Okay, we have the 0 order, second order, and first order. So these also, once again, apply to exactly what we're referring to here. So this is exponentially increasing. So if I triple the value, it becomes 9 times as fast. For this one, no matter what I do to the concentration, it is always equal to 1, so it doesn't increase. And this one is a direct relationship. Okay, any questions so far? Okay, so let's go and visit each one of these. So first one we're going to talk about is the first order reaction. How this works is if you look at a graph of the time versus the ln, so the natural log function of that concentration, then you should be generating a straight line. So this is the one that will generate a straight line for the first order. The other 2 will not generate a straight line if it is a first order, it will not generate a straight line for the second order example and the 0 order. It should only generate a straight line for one of these. So I want you to copy down this equation real quick, and we will talk about it. So if you're more familiar using this equation up here, you're welcome to do so, but this is the one that I personally prefer to use. And I'll show you a trick to kind of memorize everything here. Okay, does anyone else need more time? All right. The next one we're going to take a look at is the second order. Now, I also want you to copy down the straight line equation for this one right here. The only difference here, again, for the graph, it is going to be 1 over a instead of ln of a versus time. And because it is 1 over a, since it's an inverse, that is why this is a positive slope. Okay, so anyone else still need more time to copy down the straight line form? All right. And the last one we're going to talk about is zero order. Once again, take a minute, copy down the straight line form. This goes back to our negative slope again because we don't have it as 1 over. This is just the concentration itself versus time. Okay, does anyone else still need time to copy this down? Okay, I'm going to go ahead and share a whiteboard. This is what we're going to do to memorize the stuff. Okay. So first, I know I have A here and A here. This is going to represent my concentration. Okay. These are two concentrations. This is an equal sign here. And then we know that this is a plus sign and there is something here, some kind of form of KT. That is essentially our setup here. Okay. So most cases here, this is your A at this particular time and then A0. Any questions about that? So the way we set this up, there's always KT in the middle, there's always A0 on the right, AT on the left. So when I write this, ln of A, T, and we're going to go ahead and put the KT in the middle here, and then this is ln of A0. Now when I'm writing second order, 1 over A, T. So the setup is almost the same way. I have a KT in the middle here, plus 1 over A0. The only difference you have to account for here is all of these K's should have a negative, except for the 1 over. This is your integrated rate law. These are the three equations. This is for your zero order, first order, second order. Does that make sense now? Okay. Let's go back to our graph here. So if you look at the straight line setup that I did before, I pretty much named all of the straight line ones. So 1 over A, yes, that one is the only one that is a KT that's positive. So remember that format. AT on the left, KT in the middle, A0 on the right. Equal sign is right here, so you always set it up in that function. Okay, so essentially you're breaking into three categories here. Now, if we're looking at zero order, this is just itself. First order is ln of AT, still negative KT, and then this one is still ln of A0. If you are looking at second order is 1 over AT. And then this side is positive KT, that's the only difference. And then this side is 1 over A0. Let me rewrite that to make it a little more clearer for you. Or you know, let me just type here. That might make it a little more clear. So once again, the format is the same. AT is on the left, KT is in the middle, and then A0 is on the right. And it is only simply dependent on what you have here. So if this is just A versus time, then it is the zero order. If it's ln of A versus time, right, then it is first order. If it's 1 over A versus time, it is second order. Any questions? Okay, with that said, we'll move on to one other thing. If I went ahead and I took any detail I have here, the time versus some concentration, if you notice, they wrote the concentration as itself, right? So just concentration of A, and this is ln of A, and then this is 1 over A. So they just simply listed these out. You can do this on Excel fairly easily. Whatever your concentration is, you do the ln of A, drag it over, 1 over A, drag it over, and drag this down. So it does that calculation for you. Then you go ahead and plot this into a graph. If you look at the first graph here, this is your 0 order graph of just your A versus time. That is not generating a straight line, so this is not the one. If I look at my first order, this is ln of A versus time. This is going to be generating a straight line, so this is the correct order. And in the last one, 1 over A versus time, this is not generating a straight line, so it is not correct. So this is essentially a way to tell us, based on the information that I have here and the relationship with time, that this is going to be a first order reaction. So it's a direct relationship. If I double the concentration, I double the speed. Any questions? Now, for those of you taking the lab, I believe, I don't know if they've changed it since then, that one of your kinetics labs is going to be based on this. You will be generating about 7 different graphs, one of which is going to be the first order, 0 order, and second order. You'll see that the first order is going to give you a straight line, and then you can tell me that it is a first order reaction. And if you're doing the other kinetics lab where we're doing chickpea counts, you don't really have to do these kind of calculations here. Okay, any questions before we continue? All right, so for reaction half-life, how many of you have heard of half-life? Yes, so it is going to be a negative slope for the first order, also a negative slope for the 0 order. And the reason why is because when we look at any kind of rate that we're looking at, we're consuming the reactant. That's our main thing. So we are consuming a reactant. That's why it is generating a negative slope. Okay, so half-life, since those of you probably heard of carbon-14, things like that, it's just pretty much how much time passes before half of the substance is left. So it decays halfway. And it's exponentially. So if I had 100 of something, after one half-life, I should have 50 of that something. After another half-life, I should have 25, and then half of whatever is remaining constantly going down until it gets exponentially smaller. Okay, we can actually go ahead and calculate the half-life using our first order reaction. Now, the reason why we want to use the first order reaction is because it does not depend on our starting concentration. So if I look at this equation right here, I do not see a 0. I do not see how much I start with. It doesn't matter how much I start with. Whatever I have at that moment after the half-life, I have half of that amount, and that is it. So it's independent of the starting concentration. Now, the only one that I want you to essentially memorize and understand and know how to use in calculations is going to be first order. There's very rare occasions if they ever ask you to use second order, 0 order half-life. Any questions before we continue? Okay. So just to show you an example here, in terms of half-life, after the first half-life, whatever amount of time that might be, 0.693 is actually a constant. So it's ln of 2. So that's going to give you your constant. So if you type in natural log of 2, it is 0.693. And that is a constant. So once again, after one half-life, you should have half of whatever you started with. And then after this half-life, you should have half of whatever you started with in this spot right here. So going from here to here, independent of what you have here, you know that this at one half-life should give you half of that amount. And because we don't care about the other ones, that's why we don't really need to worry about A0. Okay, any questions before we continue? All right, so the other half-life equations, we have the first order that we just mentioned. There is a second order here, and then this is the 0 order. So I'm going to go ahead and just write in the first order here so you have that as well. This is the same as if I just wrote ln of 2 over k. So with that said, I want you to look at all 3 of these half-lives and tell me something that they all have in common. The rate constant, they all have a rate constant. Where is the rate constant in relationship to the half-life? In the denominator, right? That's correct. So here, if I look at this, if I wanted to separate this, this is just 1 over k because the k is on the bottom. This is just 1 over k, okay? This is also just 1 over k. So our half-life, no matter which one, first, second, or zero order, it's always in some related way to 1 over k. So keep that in mind. Okay, let's continue. So let's actually give this question a try. I don't believe I had done any questions on the integrated rate law, and we'll come back to that in a second. But for now, I want you to give this question a try. You're given this rate constant, this information right here. Find out what the half-life is, and then how long it takes for the concentration to get to 1/4 of the original value. So I'll give you some time to work on that. Okay, does anyone else still need more time? All right. So right away, we know what our K is. This is 9.2 seconds to the -1. Knowing that information right here, just by looking at the name, what order am I looking at? First order, okay? So we know that when we're dealing with half-life, there's dealing with the first order half-life. Okay, so let's go right into solving for the half-life. So what we're going to do here is I'm simply just going to plug into this equation. I have 0.693 already. I'm looking for the half-life. I just plugged this in. This is going to give me 0.075 seconds. Now, if I started with 100% of something, okay, after one half-life, I should have 50% of it left. In other words, 1/2. Okay. If I go through another half-life, I should have 25% of that left. So also known as 1/4. So the second part where it says drop down to 1/4 of its value, 2 half-lives have passed. So the first one, second one. If one half-life is this time right here, I multiply by 2, and that is how I get this time. Any questions on this one? If you're ever confused about the calculation, try drawing this out. It might help you. Okay, let's continue. So I want you to try another equation now. I'm telling you that the half-life of the first order equation is 20 minutes. I want you to calculate the rate constant. You can keep this rate constant in the minute value instead of in the seconds. So if you want to keep it in the minutes, it's okay as well. I'll give you some time with that. Okay, so let's go ahead and get started. What did you get at as your rate constant? I see two different answers. One of you might have changed it into seconds, I'm assuming. So we can keep it as minutes if we need to, or minutes -1 if you need to. You don't have to change that. So once again, we have the 20 minutes here, right? We know this is 0.693 divided by K. I simply swap the two of these. So it becomes 0.693 divided by 20. So if you could enter that into a calculator for me, go ahead and do so. That one should be the 0.034s, I'm assuming. Can anyone confirm that for me? Okay, awesome. So that's going to give us our rate constant, and that's minutes per -1. If you really wanted to change this into seconds -1, you can, but because they kept this in minutes, it's just easier to use this value here. Okay. So with that said, let's read the second part of the question. How much time is required for this reaction to be 75% complete? Best way to remember this, if you are 75% complete, right? How much do you have left? $25, okay? So if you have 25 left, remember you start with 100, after one half-life you get 50, after a second one you get 25. So we have essentially gone through two half-lives. And if one half-life is 20 minutes, how many minutes is it for our entire thing to get to 25% complete? It's 25% left. Two half-lives. First half-life here, second half-life there. So our total is going to be 40 minutes. Any questions up to this part? Now, questions like these, it makes it pretty easy because we can say it's 25% left, so we can calculate the difference. If you ended up with something that says 55% left, complete, so that means you have 45% left, that makes it a little more complicated. But what you can do is you can use this method to double check. So whatever you get for 45% left, it should be between these two numbers. So you know that it should be somewhere in the middle of that. So when you're doing your calculations, we can actually use another method to calculate this. Okay, does anyone else still need more time with this before I move forward? All right. Okay, so we are going to go ahead and summarize everything that we have done. So we have our rate law on the top here, units for our K is listed right here. Our half-life equations, again, the only one you really need to care about is this one right here. So I don't care about this and that, just the relationship. You know that the integrated rate law in the straight line format is this, how it looks inside of a graph, and you can see the examples on the bottom here. And this can be found in table 16.4 in your textbook, so I'm not going to spend too long on it. Anyone have any questions before we continue? Okay. So some factors that will affect our reaction rate, so how fast things move. So you may want to copy some of this down. In order for particles to react, they need to collide. So they need to interact with each other. If you have gas in one container, gas in another container, and they're not interacting, there is no way they can react. They must share the same space. So in order to mix well, we have different things that we're going to look at. Don't worry so much about the physical state as much, but it's kind of saying like certain things will not react. If you have a solid that's not really reacting with a gas, it's kind of hard to make those things interact. So first one, higher the concentration, greater the reaction rate. If you have more of it, the faster they will react, more chances they will collide with each other. Higher the temperature, greater the reaction rate as well, faster they move. So we're going to learn about a thing called collision theory. So it's going to depend on the orientation, how often it hits each other, and how often it has efficient collisions. Okay. But for now, factors that that influence reaction rate would be concentration and temperature. Direct relationship. Higher means higher reaction rate. Anyone need more time with this? Okay. So on to collision theory here. Basic principle is simply that if they collide, then they can react. If we increase the concentration, we're not increasing it in terms of sums, we're increasing it in terms of product. So the possibilities increase in terms of multiplication. So what I mean by that, particularly the example here, if I have two A's and two B's, right? When they collide with each other, the chances of hitting each other is essentially 4 possibilities, right? So this can hit this way, or this way, and this way. If I add another A in, now I have 5 and 2. So the possibilities of colliding, I can hit here, 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 or here and here. So 6 possibilities. If I add another one, it gets much more complicated at that point. Essentially, it becomes 9 possibilities, but it's essentially multiplied instead of adding. That's what they're referring to in terms of collision theory. Now, with that said, we're also going to go ahead and take a look at temperature. This does have a very significant role because you are exponentially increasing this. And the reason why is because you are not only increasing how fast the things move, but how much energy they are colliding with. So if there needs to be a certain amount of energy and the correct orientation in order to have collisions effectively. So you don't need to memorize this equation. The only thing I want you to pay attention to is when we look at the term A here, again, you don't need to know this in detail. This is known as a frequency factor. So how often these things will collide with each other. And it also needs to overcome a term called the activation energy. So there needs to be a minimal amount of energy for this reaction to go forward. Any questions so far? Okay. Now let's expand a little bit about the frequency factor. We won't go into too much detail about it. Does anyone need more time to copy any of this down? Okay. So in terms of our frequency factor, so our A value here, A is essentially determined by 2 things, the orientation and the collision. So how many of you have heard of the enzyme lock and key function? Some of you, right? So like certain enzymes can only fit because it's like it fits in a particular way. In terms of orientation, collisions must happen in a proper way or effectively. So if I go ahead and I draw you a structure here, if I have a red dot and a purple dot, okay? This is one of my things. I wanted to interact with the blue dot and the green dot, okay? So I want these 2 things to collide with each other and cause a reaction. Now, ideally, in order to do that, you would need them to collide like this, directly with each other. So this force going that way, this force going this way, when they collide, there's an interaction between these 2, okay? If you have this going in this direction like this orientation, and this one going like this is not going to cause a reaction or an effective reaction because it's just going to hit the blue and the red. Purple is going to be left out, green is going to be left out. They're not going to be separated in the process, or it's going to separate and then just float around for a bit. You want an efficient collision, so these 2 are colliding directly like this, and whatever other combination there is. Any questions? Okay. So next thing we're going to talk about is activation energy. Again, this is the minimal energy for any reaction to start. It's kind of like an entrance fee. In order to even go in, you need to pay an entrance fee. That's what the activation energy is. If you overcome this activation energy, your reaction can go forward on its own from there. You don't need to put more energy in. So this is the minimal amount of energy you need to put in order for this reaction to get to a place where it's just moving forward. So if you have a large activation energy, it's going to take a lot more energy to start this reaction, which means it will slow things down. So if you have a lower activation energy, it's easier to start the reaction and essentially increases the reaction rate. Another way to imagine this is you always imagine a hill, okay? You are on a skateboard. In order for you to go ahead and enjoy the rest of this skateboard ride, we'll say it's a little less steep so you don't fall and die. you want to go ahead and push yourself to get to the very top of this hill. Once you pass the top of that hill, then everything else is smooth sailing. You don't need to put in energy. That hill difference right here is your activation energy in most cases. Okay, any questions? All right. So activation energy is different from the forward reaction and reverse reaction. So if I drew a line for you right here again, this is usually your reactants, this is usually your product. So the forward reaction goes in this direction, reverse reaction goes in this direction. For the forward reaction, if you look at this is a short hill to cross, and then everything goes forward. But going from the reverse reaction, this is a very tall hill to cross in order to go backwards. So reactions function in the same exact way. Sometimes they favor one side over the other, just simply based on their activation energy. And the amount of energy is required to get this started. Okay, going back to temperature again, higher the temperature, more kinetic energy, more movement of the particles, so more chances of collisions. So it always increases it. Okay, in order to calculate the activation energy, the thing you don't need to worry about is everything up here. Don't bother with this here. Look down here. You're always going to deal with more than one temperature. So you never have to deal with just one temperature. Always going to be two different temperatures, and then a particular activation energy and your rate constant. Does this equation down here look kind of familiar?
Yes,
What does it look like?
from chapter 12, the vapor pressure one.
Yep, related to the vapor pressure one, the Clausius-Clapeyron equation. Very similar. That one was your ln of P2 over ln of P1. Everything was pretty much the same thing. Here you had your delta H vaporization. So the format was almost the exact same. So if you understand one of them, you have a general idea of how the other one works in terms of relationship. Okay, any questions so far? Okay. So I want you to spend a little bit of time just doing an activation energy calculation. So your job is to find the activation energy using that equation that you had, given these temperatures and given these values of K. I'll give you some time with it. It may take some setup. Okay, does anyone else still need more time with this? All right. So really straightforward. You have all of the components here. You just have to algebraically move things around and then solve for EA. Okay. So if you look here, this is my original equation. I reorganized this to get EA by itself. The -1 means that this is on the bottom. So this is underneath everything. So it's the same as if you just wrote 1 over T down here, or 1 over T minus T2 minus 1 over T1. That's what the -1 means, in case you're ever confused about that. So with that said, once you plug everything in, you get this number right here. It's a fairly large number, but activation energy is a large amount sometimes. So go ahead, take a minute, copy this down. Okay, does anyone else still need more time with this? All right. So we're gonna burn 8.314 is a constant. So R has two values. Oh, sorry. So these are your two constants for R. Okay. And the first one that you're using that mainly for temperature and energy. So activation energy, you use that one. If you're dealing with pressure, a volume, or concentration, you deal with the second one. Okay. So we're going to jump into nuclear reactions. This is our chapter 24 portion. We are really only briefly touching about this stuff, so we don't need to know too much about this. Just how to recognize certain not subatomic particles, so certain particles that are present, certain radiations, and that's pretty much the main point. Okay, so I don't need to go into too much detail about the nucleus. I assume you know this from Chem 1. Neutrons, protons inside of your nucleus, electrons are floating on the outside, okay? When you see chlorine 35, 37, these refer to the mass that is present. Chlorine already tells you the atomic number, so you don't need that information. So based on this alone, you know how many protons you have, you know how many neutrons you have. Okay, notation, again, you don't need to know this in too much detail. You know this already, atomic number, atomic mass. Any questions before I move forward? All right. So radioactivity, this is the part where you don't know yet. We are actually going to look at things that have some kind of radioactive decay. So if it's unstable, it will release radiation. We have 3 different types of radiation that we look at, and we will expand on beta some more because it has different parts. But generally speaking, we have alpha, beta, and gamma particles. Okay. Now, alpha particles, very similar to helium because you have the charge of 2. So there's 2 protons involved in that. It also has 2 neutrons. So the mass is 4, charge is 2. Beta particles, usually it is a -1 charge with a 0 mass. So it's very similar to an electron. Gamma rays are 0 and 0. These are photons. These are just pure energy. Okay. Now, the thing about gamma, that is the most dangerous one because it penetrates the most. Okay. With that said, let's go ahead and expand on each one. Again, alpha is the loss of 2 protons and 2 neutrons. In other words, ratio of 4/2, or 4 and 2 for the mass and charge. So a lot of times these are natural occurring. So this will break off into this and this piece that comes out. So mathematically, you should be able to add this up and it should still come out to the same numbers that you have on the left here. Any questions on that? So when it comes to beta decay, we have a couple of different types. Okay, and we'll expand on each one for now. So what we do know is that a neutron is converted to a proton. So in this one, this is just losing 2 protons and 2 neutrons. It's completely being lost. We're just throwing both of them out. This is where we are changing one to the other. This is our standard beta decay. And with that said, it ejects a beta particle, which happens to be similar to an electron. Any questions?
Yes, Professor. I actually have a quick question. Theoretically, doesn't this mean that it could also, that beta particle can, well, the beta decay, can it technically also become a particle with a theoretical quark, like a strange quark? And I don't remember the other two or three.
I'm not exactly sure. This does start to branch into the category of physics. So it does branch to an area that I am not an expert in.
Okay, thank you.
Okay. All right. Okay. The other beta particles are positron. So this one is the opposite. This is where we go ahead and say a proton changes into a neutron. So before it was neutron changed to proton, and then this one's proton changed to neutron. When this happens, you emit a positive charge. This is known as a positron. So this is the same as your beta, except that it is a positive charge instead of a negative charge. And the very last one in that beta particle series is an electron capture. This is where you go ahead and instead of converting into another one, you are taking a proton and you are transforming it into a neutron. So it's similar to the positron, except that you are bringing in an electron from outside. So you drag the electron from outside, you combine it with the proton, you make a neutron. So this one's not emitting anything in that sense. This one's capturing electrons. Okay. And the last one is your gamma particles. So for this one, once again, it has no charge and no mass. So it's a form of radiation that's the most penetrating. So if you were to go ahead and imagine this in terms of just everyday scenarios, alpha particles can probably get stopped by paper or clothing, whatever that is. Beta particles can get stopped by your skin and some other surfaces, and maybe some lead and metals, right? Or certain other metals and stuff. Gamma particles can pass through most of those things except for lead or one or two other things here. So you don't want to have gamma particles hitting your body. And then again, you don't want any radiation hitting your body, but the other ones can be stopped very easily by other things, such as just clothing in general or a piece of paper. But gamma particles are not stopped by that. So you need something more efficient, usually like a lead cover and stuff like that. Okay, go ahead, George, you had a question?
Yeah, so that's basically how the X-rays work then? That means it's just the gamma emissions that are being captured when an X-ray is taken?
So going back to X-rays, X-rays is based off of your electromagnetic spectrum. So it is different, it's set of frequency, things of that nature. They do block most of your body to prevent damage to the body, but they still need to take X-rays of certain parts. That's what they don't block that area. But again, going into more detail about X-rays, my extent is just I know it is on the EM spectrum. I know it emits certain radiations. Any more than that, I would go and contact a physicist.
Okay, all right, thank you.
Okay. Okay, so just a little summary of everything we covered here. Only thing you need to know is how to recognize if you have an alpha decay, beta decay, positron, electron capture, and or a gamma decay. And again, this is 24.2. All the details are here. Now, really quickly, nuclear stability. Only really thing you have to pay attention to here is there is an NZ ratio. So that is your neutrons to protons ratio. Generally speaking, it is a 1-to-1 ratio. But as we get further up the periodic table, it starts to curve upwards. So we start to have more neutrons than protons. So we have an NZ line. That's kind of like the band of stability. It starts to gradually curve upwards past N is equal to Z. And once again, last thing you also want to make sure of is any one of our elements that are greater than 83 is considered unstable, that will emit radiation. So any element above atomic number 83 is considered unstable. So looking at the NZ band, this is the NZ is equal to 1 line right here. The actual band for the elements starts to curve upwards. And we can see these are referring to number of neutrons, number of protons. If we zoom in a little bit, there is a straight line that generates a stable spot. Again, it's not 100% of a straight line. If you notice, some of them jump up and down. And then if anything is above that, it will undergo beta decay. Remember, beta decay means you're changing neutrons into protons. If it's anything below that, you tend to undergo positron decay, where you have protons changing into neutrons. And then on occasion, you have some alpha decay spread around the way, along the way. Any questions? Okay. Okay, so we are going back into kinetics. Now, just only maybe like a few more slides here. Reaction mechanisms. This is just kind of our interpretation as people on how reactions undergo what they do. Because usually it's like steps A changes to B, B into C, and then C into D. There's many, many steps along the way. We're trying to draw a mechanism that shows the steps one by one. Now, these are all estimates. There's never a guarantee that these are correct. And we have a thing called elementary steps. So kind of like if we see each piece, this entire reaction has these elementary steps. And we're looking at the first one, second one, third one, fourth one, like what happens along the way. Break it down into piece by piece. And then we have a term called molecularity. The only thing I want to bring about this entire thing is that whenever I am looking at any kind of chemical, remember how we said that the exponent here does not determine, the coefficient does not determine the exponent. This will determine the exponent if it is an elementary step, only if it is an elementary step, because again, this is our estimate and our guess. Okay. So once again, the only time, at least for this chapter, where our coefficient is related to our exponent is when we are looking at elementary steps in a reaction mechanism. So looking at here, I have just one thing here, right? 1A. So it's called unimolecular. This is to the first power. Two of them here, this is to the second power, second order. A plus B in total, it's bimolecular because there's two of them, so 1 and 1. And then here, it is 3. And once again, this only applies for elementary steps. Everything else requires calculations and experiments. Okay, so looking at this, I want you to go ahead and write an overall balance equation, determine the molecularity of each of these steps, and then try to write a rate law for each one based on what you see here. Remember, rate law only involves your reactants. So I'll give you a second to work on that.
Professor, is the first one chlorine or is it carbon and iodine? Just out of curiosity.
It's chlorine.
All right, thank you.
In most cases, they will put it as a capital I, so you'll recognize it. And plus, usually you won't see Ci2. That's not usually a combination. That would be a weird covalent bond.
Okay, thank you.
Okay, so let's go ahead and get started with this. When we're writing the overall balance equation, you just cancel things that show up on both sides. So it's pretty straightforward. You have your 3 steps here. You put them all together. Everything on the left goes on the left. Everything goes on the right goes on the right. Cancel out whatever shows on both sides. So this chlorine is here. This stays, so we don't have to worry about it. The CHCl3 stays. We don't have to worry about it. And then on the left side, HCl. Oh, HCl is on the right side. Those are split there. Okay. So everything else on the right, HCl stays, and then CCl4 stays. These all get canceled out because they show up on both sides. Any questions? Okay, with that said, it wants you to go ahead and identify the molecularity of each one of these. Very simply, first one right here, I have Cl2, okay? It's just one chlorine, so it's unimolecular. Second one, there is Cl and then CHCl3. So we need to factor that in. That's 2 of them. So that's bimolecular. Cl and then CCl3. That's 2 of them. That's bimolecular. So with that said, now let's go ahead and look at the rate law. This is where we get a little bit more complicated. So in the rate law, if I wanted to look at these individually without combining them together, just this by itself, this by itself, and this by itself, you just simply put the rate laws like this. These are the reactants on all sides, and we don't care about the product. Any questions? Again, this is this is a reaction mechanism, so we're looking at the elementary steps. All of our previous rules can be thrown out. So this is to the first order, this is to the second order overall because of the molecularity. Any questions?
How'd you figure out the molecularity?
So if I go back here, this is I'm not looking at this side, just my reactants, right? Well, how many of these do I have? How many things do I have here?
1.
There you go. This is the coefficient of 1, so that is just power of 1. This is one thing, there's 2 of them, so it's a power of 2 in total, 1 plus 1. Here's one thing. Remember, we're looking at the coefficients, so 1 and 1.
Mm-hmm.
Does that make sense?
Yeah, and then you did C, which I actually didn't understand.
Okay.
How'd you know? Wait, 1, 2, 3.
So you put 1, 2, 3 to indicate the first one, the second one, and the third one.
Okay.
Okay.
Okay. Yeah, got it.
What did you mean by the solution part? I'm a little confused. For the person who wrote in chat. This one right here or the previous one? Oh, the equation. The equation is the one right up here, this whole thing. So go back here. It's the same thing that I have in the front here. Does that help? Okay. So we've gotten to this part. Let's move forward. This is just some of the basic rules. We don't really need to worry so much about this. Just they must all add up to the overall balanced equation, must be reasonable. So nothing ridiculous. Like you can't change like let's say you're changing water into hydrogen and oxygen. You can't suddenly just add in a bunch of carbon, add in a bunch of nitrogen, do some crazy reaction, and then finally change it to hydrogen and oxygen. It has to kind of make sense along the way. And it needs to correlate with whatever rate law you determined. And just as I mentioned before, it is a hypothesis. We cannot prove if it is correct, but if it's consistent with the data, then we assume that's a good model to use for our situation. Now, is it always 100% correct? We can't guarantee that. So we're just trying to look at what steps the reaction will take as it goes through the whole reaction. Okay, does anyone else need time with this before I move forward? All right. So this is a very important one. This is called the rate determining step. I want you to imagine an assembly line in the middle of making an iPhone, okay? You got the person who is putting the software together. Then you got the person who's putting the screen on, and then you have the person who's putting the camera on, in that order. So they must put the software first, then they put the screen on, then they put the camera on, okay? Let's say the person who is making the software moves very, very slowly. They take a long time. the fastest that this entire thing can move will be dependent on that individual, especially if they're at the front of the line. Because the second that they finish their stuff, the other two can make the screen and the camera, put it on, and send out an iPhone. If we flipped it around and we said that the person who takes longest is going to be the person who makes the camera, then you're going to have a bunch of iPhones with the software ready and with the screen ready, sitting next to that person. And the fastest that the iPhone can come out is as fast as the person who is making the camera, attaching the camera to it, can produce it. So that is essentially a rate determining step in an assembly line. So in our chemical reactions, it works the same exact way. So if I look at this example, they're going to tell you which one's a fast step and which one's a slow step. If the first step is the slow step, that means it only moves as fast as what number one does. So the reaction can only move as fast as number one. So when I'm writing the rate law for this, it just simply becomes the first one, because the speed is only determined by the first one. Second one is going to be done so quick. The second that I make an NO3, right, it immediately joins with CO and then makes this stuff. So it's dependent on how much NO3 I can make in that time frame. And again, we don't write our product, we only write our reactants. So the speed of this is determined by how much of NO2 plus NO2 I can make at any given moment. That determines the entire speed of the entire reaction. Any questions? Okay. With that said, let's flip the scenario. Well, actually, we'll keep the same scenario. This is the same stuff right here. You simply write what was in the beginning. That's just these two right here. This is what determines how fast this goes, because this is the slow step. Everything else will automatically be done faster than the reaction can move. It's only dependent on this one right here. Because the second this is done, it makes something. And then every time this finishes, it makes something. So the rest of it is very rapid. This is just the slow step. Any questions? Okay. With that said, let's take a look at a fast initial step. So just as I mentioned before, the first step is very fast. It's the second step or later step that is where it becomes slower. Okay. Usually they give you two things. Sometimes they give you three different reaction mechanisms. So when we write this, the slow step is based off of this information right here, NO3 and NO. But remember where NO3 comes from. NO3, it comes from right here, okay? And NO3 is essentially the same as if I just wrote this. So the fastest that this can move is how fast I can put NO and O together, and O2 together, plus the new NO. So these three right here, because this and this are the same thing. Does that make sense? So my rate law is dependent on one of these, two of these, and one of these. So how fast this can join together. So you pretty much take everything the slow step and then whatever the reactant is from the very first step, the step before. Because your reaction is how fast you can combine NO3 with NO. And in order to get NO3, you need this stuff right here. Any questions so far? Okay, with that said, let's talk about intermediates. Sometimes intermediates are things that are produced in the reaction and consumed in the reaction. And you usually cancel them out because when you write the overall balance equation, they show up on the left side and the right side, and then you can remove them. Okay. So in their previous example here, which one of these is my intermediate? It is produced in the reaction and consumed in the reaction, and it never shows up in my overall balance equation. I'll give you a second to look at it, and then we will go through it.
HCl.
Not HCl, but take a look at it. There are two of them. I am ending early today. We're going to end around 6 o'clock, so a little bit before 6. Okay, someone said CCl3, which is correct. So if you look here, step 2 makes CCl3, right? And then in step 3, I use CCl3. So my overall balance equation will not have this. What's another one? Chlorine is correct. I make chlorine in the first one and I use chlorine in the the second and third one. So these all disappear. So they don't show up in our overall balance equation. So go ahead and cross those out. These are intermediates. Anyone have any questions up to this part? Okay, we should be able to finish all of these slides here. I'm just going to move a little bit faster. The next one we're going to talk about is a catalyst. So a catalyst does only one thing. It lowers our activation energy. So I want you to write that down. Think of this kind of like if you're trying to get into some event, there is an entrance fee. But because you are on the VIP list, you get a discount. Instead of paying like $100 to get in, you only have to pay $50. Or you know the guy, so that's why you have a discount. So it's easier to get in the door. It's easier to start this reaction. So once again, a catalyst is just simply lowering the activation energy. And this lowers both the forward and the reverse reaction. So if I were to draw you the same picture that I had here, a catalyst would essentially lower this like that. So essentially lower the overall hill. What that means, if I'm looking at the forward reaction, it is a shorter hill to climb. The reverse reaction, also a shorter hill to climb. So it affects both sides, forward and reverse. And in this scenario here, they actually have two catalysts. And essentially that means they lower this in two different ways. So it generates two different activation energies, both essentially lower than the original. And they like to refer to this as an alternate pathway. So just a quicker path to get to where you need to go. Okay, some ending reminders. So I want you to memorize those integrated rate laws and how to apply each one of these to the equation that you see. Reaction orders are determined experimentally. The only exception is when we're talking about elementary steps in reaction mechanisms. The half-life shortcut that I showed you when we go ahead and just do 100%, 50%, 25% is only good for double checking. Sometimes it doesn't always work. You may have to actually apply it to the equation and or use the first order overall equation. Now, the slow one in the assembly line is to blame. That is essentially our rate determining step. Anyone have any questions up to this point? Okay, with that said, if you do not remember what activation energy is, here is one example. Not sure if everyone understands where this meme comes from. Okay. And another one here. Okay. So we are going to actually, we still have a little bit of time, about maybe 5-10 minutes. I'm going to go ahead and get started with chapter number 17. So let me go ahead and do that for you. Okay, so let's get started. Also, just so you know, there is no poll for today, just simply because I'm leaving early and I know a lot of students are not available. So we're just going to skip past the poll for today. Your attendance is already counted. So chapter 17, equilibrium. I do want to bring this up. This is the make or break chapter. From this point forward in this chapter, if you don't understand equilibrium, there is a very large chance that you will not pass this course. Okay, so you must understand equilibrium because they will use equilibrium in this chapter, in the next chapter. In fact, in all the other remaining chapters, we will be using equilibrium. So you will need to understand that. Okay, any questions so far? Okay, with that said, equilibrium is the measurement of the rate. So how fast the forward, we learned about the forward reaction. That was everything with kinetics. Now we're going to talk about the forward reaction and the reverse reaction. Most of our chemicals reactions are reversible. So A is changing to B and B is changing to A. At equilibrium, we hit a place where the forward reaction is equal to the reverse reaction. So how fast A changes into B is how fast B changes into A. That is essentially what we're looking at here. Okay. And this is dynamic because things always change. So sometimes the rate gets affected, but it just reshifts going back to our equilibrium. So this is kind of like another way of describing this is we are always trying to go back to the homeostasis of chemicals. Okay, so an example I can give you here. At equilibrium, the forward reaction, how much NO2 I can make is equal to the rate of how much N2O4 I can make. So the forward reaction makes this much, the reverse reaction makes this much. We have our two rate constants for the forward reaction and the reverse reaction. We change this now to write this big K here. This big K is going to be used for equilibrium constant. So this is not the rate constant anymore. The rate constant is equal to these two things here. The two of them combined makes the equilibrium constant. Now, the other thing about this is the equilibrium constant is equal to your products over reactants. So if you look here, this is my product, right? And on the bottom here, this is my reactants. That is always our ratio. K, capital K, is equal to P over R. Now, what else do you notice about this equation? I'll clear the screen so you can see it. What do you notice about the coefficients? For this one, first one here is, yeah, it's 1, right? What about this one right here? What is the coefficient? And where do we see this 2? In the exponent, okay? So when it comes to equilibrium, I don't want you to get confused with kinetics. Everything we just talked about in kinetics, we still have the same rules that apply. But when we talk about equilibrium, that's the coefficient becomes your exponent. So I want you to copy this down. This is our equilibrium constant. Well, just mentioned here, K is equal to P over R. Okay. You notice here they have little a, little b, lowercase of each one. These are your exponents. They go respectively into the powers of these here. So this is your products over reactants. And then whatever your coefficient is here becomes the power or becomes the exponent. Okay, any questions so far? Now remember, I don't want you to get this confused with kinetics. So make sure you separate the two when it comes to writing down your notes. The next quiz you take is going to be just based on kinetics and not based on equilibrium. Then you will take the next quiz after that on equilibrium. But this is next week and 2 weeks from now, so I'm sure you're not thinking about it now. Okay. Does anyone else still need more time to copy this down? All right, so we will actually end this here on this slide right here, and we'll pick up the next time we meet and continue chapter 17. I can stay for another like 2 minutes if anyone has any questions. Other than that, I will essentially end our class today here. And we can cover chapter 12 and 13 in office hours next week if you want to go over any of those in detail. Okay, any questions?
Professor, is the recording going to be on Google Drive?
This recording, yes. So I've been uploading in the same place. Everyone should have that Google Drive link already. I think I shared it as an entire folder. So every time I put something in there, you should have access to whatever I upload there.
So far we have like 3 videos.
Yes, there are 3.
Okay. And also, did you get my name at all by any chance for the attendance?
If you've been joining, right, it automatically saves on Zoom, and then I just go and check there.
Okay, so the names appear there, right?
Yeah.
Okay, thank you.
Okay. Do we have a quiz next week? No, there is no quiz next week. This week you finish chapter 13 quiz. Next week you have a break from the quiz. The week after you have 16 and 24 quiz. Yes, you can bring the Alex questions during office hours as well. All right, if there are no more questions, I'm going to go ahead and end this here.
Have a
Enjoy
good
your day.
Professor. Bye.
You too. For kinetics, try all the problems out in the back of the textbook first. All right, try the problems. If you have a problem you don't understand, send me that exact question. If you have to take a picture of it, send it by email. I'll take a look at that way. Okay, I'll try my best to explain over email if I can. All right.